In this video, we're going to do an example of the extreme value theorem of the function q of x equals x squared over x minus 2 on the interval from 3 to 7. Now, this is not a function that is continuous everywhere. There's a point of discontinuity at 2, but that's not in our interval. This function is continuous on this interval. So, let's first see if we have any critical points in our interval. So our derivative, we're going to use a quotient rule. So it's the denominator, x minus 2 times derivative of the numerator, 2x, minus numerator times the derivative of the denominator, which is just 1, all over the denominator squared. Now we're going to simplify as much as we can to see what we can figure out. So we have 2x squared minus 4x minus, and this should have been an x squared, minus x squared all over x minus 2 squared. That'll simplify down to x squared minus 4x over x minus 2, the quantity squared. Now, as we noticed before, 2 is a critical point because it's a point of discontinuity in the derivative, but it's not in our interval, so we're not concerned with it. So we're going to just take the numerator and set it to 0 and see what we find. Well, we can factor an x out of there, and we get two critical points, one at 0 and one at 4. We're only keeping one of those for this particular problem because 0 is not in our interval. So we need to calculate q of 3, q of 4, and q of 7 to find our max and min. Q of 3, we're going to have 3 squared, or 9, over 3 minus 2, which is 1, so it comes out to be 9. Q of 4, we're going to have 16 over 4 minus 2 is 2, or 8. Q of 7, we're going to have 49 over 7 minus 2 is 5. Now it might be useful to write that it says a mixed number, or 9 4/5. And so we see we have an absolute max. We have an absolute max of 9 4/5, and we have an absolute or global min of 8 for this function. This is guaranteed by the extreme value theorem because we have a function that's continuous on this closed interval.